Let's start having a look at motor isolation. The best way to deal with noise in any situation is to prevent the noise from getting into the system in the first place. And the vast majority of vibrational noise on a quad comes directly from its motors and the props vibrating. The common way to try and deal with that now, aside from soft filter solutions on the firmware side, is to soft mount your flight controller, which is all fine and good, but the relative masses make that a little more complicated. Obviously it works for a lot of people in many situations, but the flight controller itself has relatively little mass compared to the rest of the quad. And whatever material you use, like when the forces are lower, when the mass is lower, it's less effective. Imagine if you had a plate of Jello and you had a feather on top of it. Like when you shake it around, the feather's going to move just right along with the Jello because it doesn't have any mass. The Jello acts a lot more rigid in that terms. If you put a hammer on top of it, the hammer is going to put a lot more resistance to the motion of the Jello, and it's not going to move at as high a frequency as the Jello underneath. So that's what we're fighting at with the flight controller. Is you have to use really soft isolation to allow the flight controller to move because it has so little mass. And if you have like if you're using a hard rubber O-ring and compressing it all the way super tight by cranking it down, you basically have no isolation at all. You've got just another rigid connection. So a great way to deal with this is the motors themselves have reasonable mass, and if we put isolation pads on the motors, we can keep, or at least try to keep, a lot of that noise from the motor shaking from getting into the frame just full stop. So we should see more effectiveness from harder compounds. I think it makes sense that there would be other benefits as well. Like if you're putting less vibrational energy into the frame, you're going to have less issues with resonance on the frame because there's less energy. Like if you try and put all of the energy into the frame and then isolate it after the frame is already resonating, then you're going to have a harder time than if you keep the energies lower from the outset. So anyway, what I've been playing with is a full custom motor mount. So I have a machined end to the arm of my frame, and I have full isolation. So not just a pad across the top, or you know, trying to center something with O-rings. And what we're looking at here is a model of the isolation pad that I used in this test. So I've got a 1mm slab on top and bottom, and then you can see the hole where the motor screws go through and the edge of the where the frame meets and this isolation pad sits. And we've got about a 0.5 millimeter of isolation material between the thread of the motor screws and the frame of the test bed here. So we've got isolation in all three axes, but we do have more isolation on top and bottom. And I'm doing this pad as a cast silicon thing right now. I have a machined mold that I casted in, actually cast it in place on the quad. And I've been playing with different stiffnesses of silicon to see what effect that has. So I've got a Shore 0020 silicon, which is extremely soft, just a little barely harder than like a jelly gummy candy, and a Shore 00 like 62, 65-ish, which is more akin to like a rubber band, and very similar to the kind of commercial gummy isolators that you can buy. And material choice is also a bit challenging because it's not just a matter of how flexible it is, but like we want to, like ideally we want a lot of frequency damping in the material as well. So it's not just that it's soft and flops around, but that the vibrational energy gets used up inside the material, so it doesn't pass energy through it. You can have something that moves very soft but still transfers a lot of energy, and that's where you'll have, you know, you have something that's at high frequency and it'll transfer at a lower frequency without losing a lot of total energy. And we really want to lose all that energy. We don't want any of the noise to come through the material at all. And I'm just using an off-the-shelf casting silicon stuff to play with, and they don't have a lot of their special formulas and materials you can get for isolation and damping that have different properties depending on the load and whatnot. So I'm starting with quite a bit of a shot in the dark, but just we can take a look and see if there's anything to see and how big a difference there is, and then we can explore other materials later. So in order to do this test, I've got a built-up quad with the isolators in place. I'm only testing one arm, and I'm testing the same arm every time using the motor test black box screen, but I'm not controlling the motor from Betaflight. I'm running it off my thrust test stand using a special test program routine, just like I run for the thrust test. So we have very repeatable, very smooth, accurate motor motion. So we'll get the same charts every single time. And of course, the first important thing to do is to look at our baseline. When I run a long log, just not touching it, not running any of the motors, this is the amount of noise that is in the system just with nothing going. So with no motors, we don't have to worry about this influencing our work. We're not seeing the noise floor of the gyro any. It is dead silent, dead quiet. We've just got this little tiny trace, you know, barely a pixel wide at the bottom, so we don't have to worry at all about the noise floor. Well, anything that we're seeing is way beyond the measurement noise that we have in the system from the gyro and the flight controller. So this graph is the unisolated motor noise, and remember, not controlled by the flight controller at all. This is an outside test ramp, so this is a very pure look at the character of the motor noise. And this particular tests an RCX 1304 motor with a 3020 DYS prop. Lightly used, not trashed, but it's definitely something that, like, I have problems with this quad over about 75% throttle, a lot of jello in the cameras and stuff like that. So it can get noisy when it gets up there, and that's really what we're seeing here. All of this low frequency stuff, this is where it really hurts us, and down where the motion of the quad, but it's not super noisy. And of course, this whole thing is looked at unfiltered. All of the filters, the gyro filter, everything is turned off. So this is the raw, pure gyro signal that we're seeing. And you can see the intensity of the noise goes up over, you know, about 100 hertz. It gets particularly bad, and then we have our peak and our spike here, right where we hit 100% throttle, and we have a lot of induced noise further up the frequency band as well. We've got this really particularly big spike just underneath 800 hertz. Now, a lot of times you wouldn't even see this in your charts. I think that the default logging rate might be 1 kilohertz or something like that, and so a lot of your default Betaflight log is going to cut off somewhere around 500 hertz, and so all of this range you might not see. And you can make out that it's not just a frequency, you know, motor speed equals noise relationship here. Down just under 200 hertz, like the motor gets quieter in this frequency range, and we have what looks like a notch filter. There are no filters applied here, so this is just a natural frequency where the noise, the motor quiets up significantly. So this is like half the intensity of the next. I'm not sure if this is a logarithmic scale or a linear scale in the black box reader, so that may be a very significant change. So let's go and look at the stiffer isolator, and you can see the character of the noise changes dramatically. We've got this huge dip. Again, it looks like we've got notch filters put in there where the frequency response of the isolator and the motor and all of that stuff, the sensitivity drops dramatically. But the overall, the peak intensity actually shifted down. Like, our peak intensity here is like just under this kind of gyro line. Our peak intensity is not that much lower at the peak, and the peak has dropped from 318 hertz, it's calculating there, to about 131 hertz. So we are seeing, especially if you watch this range where the sensitivity is a lot more in the harder of the two soft mounts, we've definitely increased the sensitivity to noise in this region compared to a rigid mount motor. But in the frequencies above that, it's massively reduced. So overall, we've actually helped things a nice bit by having that there, and we've concentrated these peaks. Our overall noise level is a lot lower, and with these concentrated peaks, although they're in an unfortunate location, if we really needed to, we can very easily notch those out, where this sort of broadband noise is a lot harder to deal with. Also really interesting to notice is all of that other induced noise in the higher frequency spectrum is dramatically dropped off. We don't have that 800 hertz peak anymore. We just have a couple little echoes that we can see here at, you know, you would imagine these would be somehow harmonics, because they, you know, it looks like we've got this same kind of frequency response here, and then slightly lower, and then slightly lower, and then it dissolves into the noise. So it's definitely, even the stiffer isolation material has cleaned up our noise floor on the higher frequencies quite dramatically. Now if we go to the softest one, we see a very different character yet again. Overall, the noise level has dropped dramatically. Remember, our peak noise on the unisolated, the rigid mount motor, is right about here at this like white gyro line. And with the soft material, we're like slightly less than half of that at our peak. And our peak noise has again returned up to 330 hertz or so. So this shape actually is a lot more reminiscent of the very rigid mount, except for this other little peak here down at around 80 hertz. Still have some evidence that looks like notch filters areas where the response is gotten a lot lower. And this particular section here, you'll notice, has moved up in frequency, so it's a lot closer to our peak there, where this dip in frequency response happened, and that's kind of interesting. And we have the same thing here, where the upper frequency ranges are all significantly cleaned up as well. You know, compared to there, we've, you know, all of this peaking at 800 is gone, and the noise in general is really quite low. Although the stiffer material here showed better high frequency isolation than the softer one, we were getting kind of more noise. Although this is all still, this stuff is inconsequential. Once you get the low pass filters on there, this like all gets completely crushed. And the other interesting thing is we can switch this over to look at the yaw noise instead of the roll, because this is the section where the motor has less isolation. And interesting, even the rigid mount, where the isolation shouldn't matter, is showing more noise than the, so if I switch there, that's the raw rigid mount noise for roll, and then if we go to yaw, our overall noise level is a lot higher. So this may be partially because the isolation, there's thinner isolation material, and we're not getting as effective isolation. It's really thin, you know, only 0.5 millimeter, and so it's very easily compressed. But also it appears that our noise level is higher, and if this could be due to the you know, the prop vibrating, or the motor being unbalanced, actually pushing it more side to side versus rocking the motor up and down. But our noise levels are higher in yaw, and the same kind of things, the more rigid isolation mount, we've got a big peak. Our overall intensity is only slightly diminished. You know, we don't have as, like here we've got some very strong sharp peaks, and then here it's a little more wispy. Our ultimate peak is just about the same, but we don't have these strong sharp bands, and it's a little lighter weight there. Lower frequency down at 131 hertz, the same that we had on the other axis, and then these large notch filter looking areas of lower response. And we do have that reduction of the higher frequency band just seen before, and on the soft side we have kind of the echo of the other one. Even though we're starting with a lot more noise, we get an overall reduction in intensity, and the motor noise, the peak itself, stays there, so it's a little more a little flatter response in the amount of isolation we're getting between isolated and very soft mount. Although we do still have an increase in low frequency transmission. So down here, probably between about 50 and 80 hertz, you can see on rigid mount, you know, the amount of level that we have there, and then when we go to the soft mount, we get a bit more of a peak, and then not quite so bad with the stiffer of the isolation material, but then we also have this bigger peak centering around 80 that we are amplifying compared to having the motor mounted rigidly. Now, the other thing that I wanted to highlight really quick is plenty of people, I'm sure, have turned on the motor test black box logging and looked at their motors just spinning them up by hand, but that's not a very repeatable method of doing it. Because it's controlled by the computer, I can do this test over and over again, and I get basically the same chart every single time. The noise moves stuff around because this is just noise, and so there's a strong element of randomness to it, but the shape and the form of these curves appears the same every time that I do the test, so it's really easy to make a change and look for differences in that shape. If I try and do the exact same test just by hand, by sliding the motor up and down, you can see how the shape of this curve changes dramatically. Everywhere where my hand sticks for a little second, we get spikes of noise emphasizing certain areas over other. This is the exact same setup in the exact same location, tested right after it, and you can see just how different this looks. So unless you have something, a very repeatable way of doing the test, sliding the motors up and down in the motor test is a very difficult way to try and judge the amount of noise coming from the motors in this sort of like static situation over a broad range of frequencies. It's a lot better for testing, like if you've got mid-throttle vibes that you're trying to sort out or something like that, you know, that's perfect for that. Go to a fixed frequency and run at that and see what it does. But here, where we're testing a ramp from 0 to full throttle and back down again, this doesn't really give us a useful thing, and this is a much cleaner picture of what's going on. We can also have a look at the same three tests in the waterfall spectrum. The peak in noise for the motor test, the test ramp that I have from idle to full throttle and then back down again. And important, of course, to notice that it is completely symmetrical, so we're not like picking up a bunch of noise and then getting stuck with it or something like that, like the motor going up, then motor coming down. The character of the noise on both sides of these graphs is the same, so we don't have to worry about problems with the test or the recording in that regards. We also do have, once you hit this kind of just above the 75% throttle range, probably a broad spectrum of noise through all frequency bands compared to just below that. Like at mid throttle, it's a lot quieter down low and up high, and then once we hit that noisy section, the noise is all over the place, in addition to the very strong peak signal from the actual prop itself. The middle one is the more rigid material, and you can see these darker bands here are going to be what look like the notch filters in the black box log reader that we were looking at. And even very intense noise of the motor vibration itself is attenuated very, very strongly right in that range of frequencies where it just doesn't like passing energy through at all. So this is very well damped at this one particular frequency. The full throttle section is also quieted down quite significantly, even with the stiffer isolation material. And it hasn't really done anything about these kind of echoes that we're seeing up through here. And originally I was thinking that this might be artifacts of the conversion from the gyro data into the audio file to get this into the spectrum analyzer, but given that that we saw those kind of echoes in the black box log reader as well, those little kind of harmonic looking things, that's probably exactly what we're seeing here. These are the harmonics of the system dropping down intensity as they go up and spaced out. And so you can see that they're still very clearly there, but not nearly as strong as they were. And then in the far right, we have the soft motor isolation material, and we've got more noise at that peak. So it's we've got the softer material definitely looks like our broadband noise, which is kind of what we saw in the black box charts as well, that it still had a very broad frequency response, and that is largely coming from this section right here near full throttle, where we get noise in all frequencies in addition to the strong one. And it hasn't dampened down the peaks nearly as much, and we can adjust the contrast a bit and take a look at the relative intensity, but we're not seeing an even reduction in noise, where here we've got that section where it's really rejecting the frequency and quiets up, but we still have a strong response down in the lower half of the throttle. And in the soft one, the soft mount, we've definitely lost a lot of the strength of the motor noise in the lower range of the throttle. So if you look at just this kind of left section here, over that section of really bad motor noise, you can see that where we've got the strongest amount of noise in the rigid system, and it definitely increases it's increasing the strength over a broadband in the rigid mount. And in the stiff motor mount, that we do have an improvement, even though the peak is largely the same. And in the soft motor mount, we have a reduction even further in the kind of background noise, and we're getting a reduction in the peak frequency response from the motor itself, even though the peak of the throttle itself is still a little noisy. Now I can also drop the contrast on this and look at just the peak of the motor noise. So this is the direct noise from the motor, not stuff that's induced or the broadbands that we're seeing. So this is the absolute strongest intensity noise coming at any particular time. And you can see in the rigid mount, we have a pretty strong response throughout the most of the range. We have a little drop in a response here, at probably about 1/3 throttle, and then actually right at those bands where we cross into that particularly noisy section, that broadband noise is so strong it's actually competing with the kind of lower amounts of direct motor noise itself. The rigid mount, you can see a lot more clearly those sections of poor response, which is good. We want poor noise response. And the peak itself has been knocked down ever so slightly. It's not quite as bright, not quite as strong as the peak there, although our lower frequency response has been amplified actually compared to the rigid mount. We're getting a stronger response between kind of third to mid throttle or so. And then on the soft motor mount, you can see just how much of that attenuation we're getting through most of the band, and then the peak is not that much attenuated compared to the harder isolation material, but isn't any worse than it was before, and we're still seeing a reduction compared to the rigid mount itself. So this has cleaned up a lot of the direct noise with the soft material. And then this set of charts is the exact same thing, but looking at the yaw instead of the roll, just like we did before. And there's not really anything new to see here, except the character of the noise is a little different. Certainly the broadband nature of the peak throttle noise reflects a lot more strongly in the softer motor mount, and we've got this kind of batch of low frequency response that's really kicked up in the very soft motor mount. that doesn't appear at all in the stiffer motor mount, where we've got the harmonic kind of looking bands, where we're getting fairly strong response up and down, but this is very, very broadband. So perhaps this is something where this is too soft, and we're seeing something that's the isolation material is too soft or too thin, and it's getting hit or compressing too much and transmitting a lot more of the basically unisolated noise just because it's too soft there. It might be interesting to try and make the ring isolation thicker so that it's the same as it is on the top and bottom, and see what sort of effect that has. But overall, I hope that gives kind of an impression, just the relative scale, how much isolation we can actually get from just a little bit of silicon. And if we have like troublesome frequencies, you can tune a physical vibration isolation system just like you would a soft filter. I mean, we have these frequencies where the isolators obviously have areas of reduced responsiveness, and if we can figure out how to design around those or material choice to do that, we can get much more specifically targeted isolation builds compared to just like random guessing and throwing stuff at the wall. Although the soft isolation material definitely looks like it's the strongest at isolating in general, it's also not super durable. It's because it's so soft, the particular motor mounts that I have cut into it quite easily. So I think I'm going to be experimenting more with this stiffer material, because it still does a really good job at knocking down quite a lot of the vibration without being quite so flexy. And then hopefully, if I get some time, there's definitely other, there's a wide range of materials or stuff we can go even stiffer yet. Like, it would be nice to look at some like 70 or 80 durometer, like basically the equivalent of like a nitrile rubber O-ring that are commonly used. I've got those on other ones as well, just not in this format. And other castable materials as well, like their polyurethanes are also used in isolation, mount vibration isolation and stuff like that. So it would be interesting to play with some of those and see what sort of difference it is. But that'll do for now. We'll have to see where this winds up in the future.